So we are trying to solve this system of 5 equations in 5 unknowns. We started with equation 3, and we said if equation 3 is true, that either z is 0 or mu is negative 1. Let's deal with the case that z is 0, and let's see how that would help me out. The only other equation I see with a z in it is equation 5. So I'm going to go to equation 5 and say if z is 0, well then y squared is 1, so y is plus or minus 1. So I sort of have two subcases here. I've got z equals 0 and y equals 1, or z equals 0 and y equals negative 1. With both of those, I've taken care of equations 3 and 5. Let's see if we can keep going and find a solution to all 5 equations. Okay. Notice, once I know y, I can then solve for x. So if y is 1, then equation 4 becomes x minus 1 equals 1, so x would equal 2. Now it might be tempting to stop here, because I've got an x, a y, and a z, but I don't necessarily have a solution to my system of 5 equations in 5 unknowns, because I've only used 3 of the equations. If there's a mu and a lambda that will make all 5 equations true, then great, I've got a point. If not, there's no solution for this particular scenario. So let's see what I haven't looked at. I think I want to jump up to equation 1. If x is 2, then lambda is going to be 4. Oh, that's lovely. Okay, so now I've got an x, y, z, and a lambda, and 4 of my equations are true. I'm just hoping I can plug into the 5th equation, which is equation 2, and find a mu that's going to work. So equation 2, 2y, let's see, y is 1, so that becomes 2, is equal to negative lambda, so that's negative 4, plus mu times 2y, and y was 1, so times 2. Oh yeah, I can find a solution. I can see that I don't really care what mu is, I care that mu is. If I were to add this over, I would get 6 equals 2 mu, so mu would equal 3. So that tells me I did now check equation 1, 2, 3, 4, and 5. But if you stopped when you just had x, y, and z, even though this point works, you didn't prove it. Okay. So we've got that possible point. So let me just start a table of values up here with x, y, and z, and then f of x, y, and z. We'll see if we've got enough space. We just got the point x was 2, y was 1, and z was 0. Now, if z was 0, that made equation 3 true. We had 2 possibilities for equation 5. Y could be plus or minus 1. Let's explore now if y is negative 1. Again, I think I want to look at equation 4 next and say that means that x minus negative 1, or x plus 1, would have to equal 1. So x would have to equal 0. Okay, let's now look at equation 1. If x is 0, that means that lambda is 0. So the equation that I haven't looked at is 2. All I need to do is make sure that there is a mu value that will make that 5th equation true. So let's see, 2y would become negative 2. That's going to equal 0 plus mu times 2y is negative 2. Oh, beautiful. Mu is 1. Okay, so that worked. So that gives us a second point. Whoops, I wrote 21z here. I meant to write 210. So for this point, z was again 0, but this time y was negative 1, and that gave us that x was 0. Okay, so those 2 points I got from making equation 3 true by having z be 0. All right, I'm going to erase this work just to clear up some space, but we determined the only other way that z could be true is if mu was equal to negative 1. So let's explore that possibility now. Now, if mu is negative 1, equation 3 is true. Okay. if mu is -1, let's see, what does that tell me? Let's see. The other place that mu occurs is in equation 2. So it looks like I want to go there. So that's going to give me that 2y is equal to negative lambda plus mu times 2y. So minus 2y. So 4y equals negative lambda. Y is going to equal negative lambda over 4. Okay. That doesn't give me a numeric value for it yet, but that's going to give me a nice relationship between x and y, because I can also describe x in terms of lambda. So if I combine this with equation 1, that's going to give me that y is negative 2x over 4, because I just replaced, what did I do? I replaced lambda with 2x. That's what I did. I'm sorry. Lambda is the same thing as 2x, so I replaced lambda with 2x. This, of course, becomes negative x over 2. Okay. So that gives me a relationship between x and y. Now, I think if I plug into 4, since that involves x and y, that's going to give me numeric values for them. So, x minus y becomes x minus negative x over 2, that's my y, and that's got to equal 1. So that's 3/2 x equals 1. Okay, x is 2/3. But once I have that, that means that now I can plug back into my characterization of y. Y is going to be negative 2/3 divided by 2. Well, dividing by 2 is the same as multiplying by 1/2, so y is negative 1/3. Okay. So now I've got a value for x. I've got a value for y. And I've looked at equations 3, 2, 1, and 4. So there are two things that are missing, and I think we're going to get them both by looking at this last equation. I need to know what z is, and I need to make sure that equation 5 is true. Okay. So if y was negative 1/3, plugging into equation 5, negative 1/3 squared becomes 1/9 minus z squared equals 1. Oh, that's not going to work, because notice that means that negative z squared would equal 8/9. That's not possible. That's positive, that's not. So there is no solution if mu is equal to negative 1. That's not to say there's no solution, because we got a couple of points here from case 1, which was if z was 0. But if we allow mu to be negative 1, we reach this contradiction that something that isn't positive is equal to 8/9, which I can pretty clearly see is positive. Okay. So a little bit tricky when you've got 5 equations and 5 unknowns, but strategic laziness, start with the simplest equation. Okay. All right, so now these are my two possible locations for a max and min, so I'm just going to plug them in to this particular function. Okay. So if I do that, let's see, x squared is 4 plus y squared is 1, 4 plus 1 is 5. Okay. If I plug in this point, x squared is 0 plus z squared is 1, y squared is 1 plus z squared is 0, I'm going to get 1. That's the biggest, so that's my max. That's the smallest, so that's my min. And we were told for this problem that the max and the min did exist. Okay, we were certainly working with a continuous function, and if our constraint curve ends up being closed and bounded, the extreme value theorem would guarantee this. I probably should have mentioned, I can't remember now if I did, we've been doing this for so long, can't remember if I mentioned that we are told in this problem that a max and a min do exist. So the answer would be f has And of course, it's understood this is a constrained max of 5. It occurs at 2, 1, 0. And F has a min of 1. Again, that's a constrained min. And it occurs at this point 0, negative 1, 0. Good stuff.